So again, given some possible allocation set as a function of the risk and return of the two assets and the diversification, the correlation coefficient between these two assets, we have an allocation set. Then, given a risk-free, we want to know where we want to be on this line, and the answer is we want to be on this line at the exact spot which produces the steepest sloped capital allocation line, the steepest sloped cal. We can be anywhere. We can say A, you can see that A is possible, but A isn't as good as P. P is the best. So what we want to do is we want to choose the weights of W1 and W2. This is where we're going to sit on that black parabola in order to choose P to maximize the slope of the capital allocation line. And I'm going to show a little bit of the math here. We'll go a little bit quickly to get through this. Again, I'm not so concerned about the derivation. I want you to see it. I'm not going to make you repeat it. I'm not going to make you prove this. But I'd like you to see the derivation again so that this isn't, the resulting equation isn't magic. So we're going to choose W1 and W2 to choose P to maximize slope. But since W1 plus W2 is equal to 1, I can actually get rid of the W2's below, and so we can rewrite this slope equation as a function of the elements of our investment universe, asset 1, asset 2, and the risk-free, with just a single choice variable W1, since choosing W1 means we also choose W2. So we start with our slope equation, and that's going to be the expected return of the portfolio minus the risk-free divided by the portfolio standard deviation. This is the Sharpe ratio for whatever P we end up choosing. We don't know which P we're going to get, but this is the P we're going to choose. This is the P that we end up choosing, and this will be its slope. And I know that the expected return of this portfolio is going to be the weight of the first asset times the return of the first, weight of the second times the return of the second. We'll swap out in a minute. And the risk in the denominator of the slope or Sharpe ratio is going to be our standard portfolio risk equation, W1 squared sigma 1 squared, W2 squared sigma 2 squared, 2 times the rho, the correlation, the weight, the risk, the weight, the risk, and then we take the square root of that to give us our standard deviation. And so substituting in the purple for the purple and the yellow for the yellow, I end up with this equation. And also noting the places where W2 shows up, I can substitute those out as well. And so now I have the slope equation as a function of a single choice variable W1 and our investment universe, which is the risk of one, the return of one, the return of two, and the risk-free, the risk of one, and the risk of two, and the relationship between them. So now we have the slope as a function of the risk-free rate, the return and the risk for assets 1 and 2, and the diversification between assets 1 and 2, the correlation coefficient. And we have this as a function of a single choice variable. So I've just rewritten this equation with just a single choice variable in red. And we need to maximize the risk-return trade-off. In other words, we need to maximize the slope, or the Sharpe ratio. And so to make this as big as possible, to find the W1, which is what we get to choose to make this as big as possible, we take the first derivative of this equation with respect to W1, set it equal to 0, and then solve for the W1, which will now be W1 star. And I'm not going to do it because it's a bunch of awful algebra and calculus, and we can take the second derivative to show that this is really a maximum, and again I'm not going to do that, but this is what we get, and we get this awful equation. And I'm not going to make you plug this in a calculator. We'll do this on a computer, otherwise you're going to get too many fat finger errors. So here is what I have. I have W1 is equal to the risk premium of 1 times the risk of 2, the risk premium of 2 times the correlation and the standard deviations, and then all this junk in the denominator. But I have all these values. I know that the return of asset 1 is 13, the risk of asset 1 is 20. I know that the return of asset 2 is 8, the risk of asset 2 is 12, and the correlation is 30, and the risk-free rate is 5%. So I plug in all these numbers, and I get W1 is equal to 0.6 or 60%. And the way I interpret this value is that a portfolio between asset 1 and asset 2 that has 60% in asset 1 and 40% in asset 2 gives us our optimal risky portfolio. And this is really important. P is optimal because it gives us the cal with the steepest slope. And so back to the graph here, when I'm trying to figure out where I want to be on this line, I now know that I want to have 60% of my money in asset 1 and 40% of my money in asset 2, because that's going to produce the P that has the steepest sloped cal, or the line that is just tangent to this portfolio allocation. And so I've solved for the weight of asset 1, 60%, the weight of asset 2, 40%, that gives me the spot on this line with a risk-free rate of 5%, that gives me my steepest slope or highest Sharpe ratio capital allocation line. So what do we do with this? How do we interpret this? Well, we know that the 60-40 gives us the optimal slope. And why is this the optimal portfolio? Well, if I calculate the expected return of P using W1 and then W2, I could see I get 11%. And if I calculate the risk of P along this axis, plugging in the 60 and the 20 and the 40 and the 12 and 2 times this correlation coefficient, and then there's the weight and the risk and the weight and the risk, and I take the square root, I get 1420. And so this 11, 14, 20 portfolio is the portfolio that, when combined with the 5% risk-free, gives us the steepest sloped capital allocation line.